All right, so again, greetings to everyone. We're going to get started. There are quite a bit to cover today. First, let me point out that the test that was scheduled for this afternoon has been rescheduled to Tuesday of next week. And this was to allow for the tutorial that will take place today or shortly. All right, so please take note of the new date for the test. We're going to proceed to start lecture 3, which is part 2 of mathematical modeling. And then we're going to break for a session for you to share whatever concerns you may have up to this point. All right, so let's get started. The presentation that I'll be doing now will cover aspects of mathematical modeling to include block diagram model reduction techniques. We're going to look at MATLAB as a simulation tool, and I may not be able to start state-space modeling, but we'll definitely be covering at least the first section of the outline here, which is block diagram reduction technique. So let's get started with block diagram reduction technique. Now, control systems, or should I say systems in general, are often represented with a block diagram, and that's no different for control systems. All right, so systems in general, engineering systems, physical systems can be represented using block diagram. Right, and therefore control system, being a system, can also be expressed in terms of a block diagram. Now, these systems may have many feedback loops, and it becomes very complex to understand and to perhaps appreciate the whole system. And so there's the need to simplify a complex network of subsystems into one single block that will represent the entire network. And so this is achieved through block diagram reduction. All right, and we're going to now look at block diagram reduction techniques. Okay. So when I speak of block diagram reduction techniques, I'm talking about rules that govern the reduction of block diagrams. And there are about 6 of them. And we'll start with the simplest of the rules. Now, the first one speaks to cascade blocks. And when we hear about cascade, what should come to mind is series, blocks in series. All right, remember that the Laplace transform is a method for converting time domain functions into frequency domain functions. And when we speak of a block diagram representation, we're talking about blocks that, especially with controls, right? So let me be careful here. When we speak about block diagrams in control systems, the function in these blocks are in the S domain. Okay, so you notice in the first rule, which is the cascade block reduction, we have capital H, capital G, all right? And these are representing Laplace functions for the different subunits. So there are 2 subunits in this block, and they're in series. Now, the signal that goes into this system is X, and the signal that leaves the system is Y. Now, what is proposed here is that, in such a case, the simplified block diagram, that is again one single block in this particular case, is a block that says G times H, right? G times H. So what has happened here? The simple procedure here is that the blocks are multiplied. When I say the blocks are multiplied, I'm talking about the transfer function for each block. You simply multiply the transfer function for each block. All right, this is simply the rule for cascade. Now let's look at another rule, and this is the rule that is concerned the movement of what we call a summing node. All right. So when we speak of a summing node, we're speaking of the little circle there with the plus and minus sign they're attached. Okay. So summing node is right here. Okay. So notice that there are a number of signs there, plus, plus, minus. Now, how do you treat with this? What we're showing here is a combination of two possibilities, and we're showing them at the same time. Now, for a summing node, these are the two possible two possibilities, right? You could have plus and plus, or you could have, right, plus and minus. All right. So what we're doing here is we're actually showing the two cases. Plus is at the top because this is all at the top. Here, I'm talking about right here, up the top here. Now, for the lower section, we're showing plus and minus. It really means plus or minus. Whether it is plus or minus, it's the same procedure. So let's get into the procedure of moving this summing node. Now, to better appreciate what is happening, there are two signals going into the block G. And let us take, first of all, the possibility of a plus and plus node. All right, so I'm going to try and put a mark over the negative. All right, that's what we're looking at right now, plus and plus. Can somebody open the mic? I'm not able to, well, let me bring this up. Could you just use a raise hand feature? And I'm going to ask somebody to tell me what you believe the output of this function to be. In fact, let me go back to the first rule, and I'm going to ask the same question, right? What is y equal to? Can somebody just indicate my raise hand feature and just let me know what is y equal to? Anybody tell me? At least try. All right, go ahead, Milton.
XGH.
All right, so Milton says, thanks for that feedback, Milton. Milton says XGH. And that's in fact correct. What Milton has done here is to multiply the input signal by the transfer function of the block. And that is in fact correct. Y is equal to XGH. And I'm sure that Milton also recognized that the transfer function definition is Y over X. Okay, Y over X. And so what we have here is Y over X. If you should transpose Y over X would be equal to G times H. All right, so it's adding up. Now let's come back now to the second rule. What do you believe Z is? Again, use a raise hand feature, please. What do you believe Z is equal to? All right, Milton, please go ahead again.
Is it XG plus no X plus YG?
All right, so you have to help me out with that now. Are they coming to you, Duncan? Well, Duncan lowered his hand. Is it? Let's go again with that for me quickly. Z equal?
Z is equal to X plus Y multiply everything by G. So G.
Oh, I see.
G.
Great. Excellent. So that is in fact correct. Thanks again. So what we're seeing here is that we're taking this input. The input is actually X plus G. I'm sorry, X plus Y. And X plus Y is now fed into G, and the result is we just simply multiply the input by the transfer function, and that's exactly what was done here. Now, what we need to appreciate is that whatever this system here is doing, the equivalent or the the equivalent, which is the one where we have removed the summing node from the input of G to the output of G, must be saying the same thing. Yes? And so we're going to now examine to see if that's the case. So I'm going to attempt to write it on the slide. We're having a little space. Can you now recognize that what is coming here is x times G? Yes, x times G. So x times G is then going to be added to what? Y times G. Yes. And that is equal to Z. Now, if you look at the expression for this side, which is right here, and the one here so as well, for here, you'd say the two functions are equivalent. This is equivalent, right, to the one that I've just written here. If you expand here, you would say that it's the same thing as this. Therefore, the representation is in fact equivalent or correct. Okay, it's given a correct alternative form for the original expression. So one way to look at it is that if you were to remove the summing node, which simply means to remove y, take y out and put it down here. All right, so if we're taking y from here and putting it here, if we were to leave it as such, all right, so this is no longer here, all right, plus here, so it becomes, what would be there right now, just putting it there without any block before it, what would have is x times G plus y equal Z. And I'm sure you recall what was there before. It was xg plus yg. Milton just explained that a while ago. I just alluded to that. So if we were just simply to move the summing node without putting any block before y, as we're seeing here, this is what would end up with, sorry. And we would say that it is not equivalent to here. It's not equivalent. And what would make this expression equivalent is if we put the function g, or multiply the function g by y. Hence, we do this. And we end up with what is right here. Okay. Now let's move on to the third reduction rule. And this time, we're moving the summing node from the input, sorry, from the output of the block to the input. All right, so we're moving the summing node from the output to the input. And guess what? We see a reciprocal action taking place here. So y is now placed behind, or should I say before the block. So it's now placed here. So the signal y in the first instance was not passing through G, but in so putting the function or the summing node at the input of the block, the signal y is now passing through G. So to reverse that, we have to put a block y, 1 over G before the input signal y to cancel the effect of it passing through G. That's one way to look at it. Again, you can do a similar thing that I did before for the other two blocks to show the mathematical relationship between the two systems. Now, as I proceed, you need to be aware of these rules and to apply them in the simplification of block diagrams. Okay, let's move on to the fourth such rule. So here now we're interested in moving a pickoff point. So we saw where we moved in the last two instances, we moved a summing node, right? In one instance, we moved the summing node from the input of the block to the output. In the other, we moved from the output to the input. This time, what we're doing is to move a pickoff point. And a pickoff point is where a signal is just simply, can I say it? Pick off. That's not we're simply extending a signal. Let me not joke around this. So we're basically extending a signal. All right. So y is actually the signal that is here. I was simply extending it to provide it at another point. Right. So I could even do this once more. Not a pickoff point. What are we doing? We're just simply extending the signal Y to some other point. Okay, so whatever is here will appear at all points along that pickoff point. Okay, so now what we're interested in doing is to move this pickoff point from the output of G to the input. Okay, so what we're picking off here was Y. So if we were to say, okay, let's put Y here, let's do that. Put Y here. Clearly, this is not Y, that's X. So the question is, what do we know to make this signal actually equal to Y? Y was equal to what? X times G. All right, X times G. So therefore, as you can see here, the function G was inserted between the signal X and Y to create that new signal Y. All right, so we move the pickoff point from the output of G to the input, and the function must remain the same. As I pointed out earlier, if we just simply move the pickoff point and not do anything else to it, what would be seen is not Y, but X. The question is, what was Y before? Y was actually equal to X times G. So to fix that, we just simply put G here, right? As we're seeing on the equivalent network. Please feel free to raise your hand if you have a concern about any procedure that I'm going through here, as is the case with any other part of the NIST that I'm presenting on. All right, so let's now look at, this is what now the fourth rule, and this time we're moving the pickoff point from the input of the block to the output. Here we're seeing that what we have is a pickoff point at the input, and this pickoff point signal is X. Or if we were to put the pickoff point here and call it X, that would not be true, because this would now be Y, and what we're interested in is X. So if we were to write an expression, okay, fine, Y is equal to X times G. Therefore, what we need to do, since we're getting Y here and we want X, right? We want X. I'm sorry, let's go again. We want X here, sorry. But what we're getting is Y. How do we fix that?
Sir.
X. Yes,
sir.
Go ahead, please.
Yeah, can you use up the eraser, sir? Because sometimes when you mark up the board like that, it kind of confusing and lose track of some of the things that you're trying to demonstrate. So I'm wondering if you could just use up the eraser.
Yes, in what case right now? In what case right now? All right, because fine. This is all right, fine, no problem. Let's go again. So what I'm trying to do here is to provide you with a means of remembering the rules. All right, and this is something that you perhaps have to do on your own time, but I'm just giving you a kickstart on that. All right, you need to know the rules. So here I'm showing you, as I've done in the previous cases. All right, what we're seeking to do here is to move this pickoff point called X to the output. Now, if we were just to move the pickoff point and do this, what signal are we actually getting? We're getting Y. Go ahead, Richard. Richard?
Yes, sir. What exactly is the pickoff or the pickoff point? Is it just the output?
Oh, I thought I spent some time discussing that. I said the pickoff point is just simply you extending a signal. So if I want to extend a signal at X, I just simply do this. That's a pickoff point. It simply extends the signal. All right? So you could put a pickoff point anywhere and want it to extend the signal, like you have a wire connected to a circuit. And if you wanted the connection to, let's say, a particular point on the circuit to be extended somewhere else, you put another piece of wire there. So it's a similar way here in that, I'm coming to you, Antonio, that we are picking off a signal. So the pickoff point is just simply you placing a line attached to the point in the system that you want to pick up that signal, or to extend the signal. Is that okay?
Yes, sir. Very much. Thanks.
All right, good. So, Anthony, go ahead, please.
Yes, sir. I understand completely what you're doing, but I have this question. I'm realizing that you're basically duplicating the signal, meaning that you're processing Y 2 times and you're processing X twice. So in what instance would you have needed to do this? As in, why not just take it from the output? Why you need to have it from the input, or why you need to have it before the block?
All right, so if I understand your question, thanks for your question. If I understand your question, is that why do we need to be moving these pickoff points before and after the block? What's the purpose of as a question, right? That will become apparent in the next slide or next couple of slides, all right? But for now, I want us to understand and appreciate the rules that are presented here. These rules are like the rules that govern circuit analysis. And they're going to be important in simplifying complex block diagrams, okay? So we should be able to prove, or should I say you should recognize that these two systems are equivalent. Yes. Clearly, we would see that when we pass y through this function, what we end up is with x, right? Based on the fact that y is equal to x times g. Now let's go to the very last rule in the presentation here. And this is called a feedback loop. This is called a feedback loop. Now again, what is presented here is the scenario where you have two possibilities. Let me go again and point. I'm pointing to right here in particular. Notice that you have plus at the top, meaning plus is this attached to the signal x, and then you have plus minus at the lower end. What it simply means is that we're looking at the two scenarios in one rule, in one go. Let us first take the scenario with plus and plus. It's called positive feedback. So I'm going to now take the marker and I'm going to mark out the negative. So we're looking at plus and plus. And I hope by now we recognize that there's only two signs can be there at any given time. You can either have, as I said before, you can either have the case plus and plus, or plus and minus, right? Plus and minus, right? So what we're focusing on right now in the first instance is plus and plus. How do we then interpret the result on the right? Again, what I just did was to mark out the lower sign in the plus minus thing on this side. What I'm going to do on the opposite side is to mark out the lower sign as well. Can somebody indicate to me what sign on this block should I be marking out? Marking out the positive or the negative sign?
Negative, sir.
Why you said negative? Remember, I was saying to you, you mark out the lower sign. That is how the rule, that is how we try to do it, and that is how it is understood. So I just marked out, Jordan, the lower sign on the left hand side. I need to mark out the same one on the opposite side, which is now going to be the positive. Therefore, for a system that has this kind of a feedback arrangement, the rule is what? G over 1 plus, I'm sorry, let me go again, not plus, because the signs it's a little bit down, dim, or should I say it's not very clear, but let me see if I could, what you actually have here is G over 1 minus GH. That is the equivalent representation for this representation here, plus and plus. If it were, yes, the opposite now, which is plus minus, which is called negative feedback, because you have a negative in the feedback loop. Yes, negative feedback. Then what we do is to cross out the upper sign, right? And so it becomes G over 1 plus GH. And this can be proven. All right, this can be proven. Okay, this can be proven. If I may, for the benefit of those who may be on the curious side, it's something you can actually prove on your own, but let me see if I could quickly go through this without, I don't have much space, but I'll try. Go ahead, please.
What I was thinking about, if you remove the plus from the bottom and say then x minus h times g equal y, would that be correct?
All right, so you started the process. So we're trying to simplify the block. And so we could say what signal is going into G? Don't close your microphone. Just continue, please. What signal? If we're saying, what did you choose again? Plus and minus. So we're crossing out the plus on the lower side. So it's negative feedback.
Yeah.
So now what would be the signal entering G based on what we have here?
The X minus H.
Thank you. Not just X minus H. You have to be careful. X minus, remember H is not a signal now.
Yeah, the feedback from H.
Which is what? X minus.
Which
Let me.
the input is Y, so the input is Y and the HY.
Good. So the X minus H times Y. Doesn't matter which one come first. It's multiplication. So that is a signal going into G. Therefore, what is Y equal to?
Yeah, so Y equal X minus HY times G.
Okay, good. Times G. All right. Now, do you recall what the transfer function? Remember now, what we wanted is to represent this block here, this loop here as a single block. And again, apologies on the space challenge, a single block. And what is going to that block? Signal called X. And what is coming out? A signal called Y. And if we were to keep this transfer function as a symbol, let's call it, we have G there, so we can't call it G. Let's call it G prime. All right, G prime. What is G prime equal to based on the expression I have up here? G prime is equal to what? Y over X. So what we now need to do is when we come down here, we need to just simply write that Y over X, and whatever comes out, that is the transfer function. Is that okay? So we have to expand, and let us see if we could do it with the limited space that we have. That's going to be X G minus H Y G. Do you agree? In terms of expanding, that's not hard, so that's clear. So what we're going to know is to group like terms, group the terms. All right, we're going to know this is H times Y G. Group the terms. So we have we need to put Y's together. So let's just move over the HYG. That now becomes, all right, so bear with me here. Let's come over here. It's now becomes, sorry?
I'm not seeing what you're writing.
Oh, you're not seeing that at all?
Not what you're writing right now.
No, what's the last thing you see? Are you seeing what is here?
I'm seeing Y equal XG minus HYG. That's
And
right.
that's fine. That's fine. There's nothing else there yet.
Okay.
There's nothing else there yet. So we're now going to take over the Y, the HYG. So it becomes, I'm actually going to skip here, factor out the whole thing. So it becomes 1 plus YG equal XG. Are we seeing that? You can have a piece of paper and looking at what's going on, but that's what it's going to be equal to. Now remember what we're talking about. We want to achieve this. When we do that, we know we have the transfer function. So we need to now have Y over X. So we now need to do what? We're transposing, right? We want to have Y over X. So we need to take this aspect here, or this component, this term, and carry it over to the opposite side. So it becomes, again, bear with me with the space challenge as I navigate the space. Milton, I'm coming. Go ahead, Milton. Have a comment.
Sir, wouldn't that be Y over bracket 1 plus HG close bracket equal to XG?
I'm sorry, could you go again, please?
On the bottom left corner, sir, you have
Mhm.
Y open bracket 1 plus YG close bracket equal to XG. Shouldn't the Y in the bracket be a H instead?
The Y in the bracket be a G.
H.
All right.
H instead.
It should be a H. All right, let's look at that. And that is in fact correct because we're factoring out. Thank you for that very much. So what we did, we factor out the Y, so it's H times G. All right, so thanks for that. H times G because we factored out the Y. Okay, H times G because we factored out the Y. So let me go one more time. We're starting out with what is here, and we're grouping the like terms. There are two variables in the function, X and Y. So we're grouping the Y variables. And so when we care about HYG and factor out the Y, we end up with 1 plus HG. That is equal to X times G. Now, when we begin to express the function in this form, Y over X, you can hopefully see that we need to take this section here, or this factor, over the equal sign, and take the G over on the opposite side. All right. I'm sorry, the X on the opposite side. So long and short, what I'm saying is this. I'm going to go up to the top now. Is that when we have Y over X, it is going to be equal to, can you open your mics and tell me, somebody? Jordan or anybody else who want to speak to this?
Sir, G over 1 plus HG.
G over 1 plus HG. All right, thank you for that, Jordan. So that is the simplified expression, and I'm hoping now that when we come to look at what the rule says, we're seeing the same thing. All right, remember what we're doing here is we erase the upper sign here, and that will correspond to erasing the upper sign on the other side, so it becomes G over 1 plus GH, which is what we have here. All right, now as I said before, I'm doing this so you can have an appreciation for the rules. All right, this is not something that we just pull out of a hat, but they are equivalent. Okay. All right, so let's move on to the application of these rules. So here it is that we have a block diagram, and this is what we call a block diagram with 2 feedback loops. Now, can somebody tell me the blocks in the inner loop by stating the transfer function of the individual blocks? Use the raise hand feature, please. State the blocks that are in the inner loop by stating the transfer function, or the symbol, or the letter symbol that represent the transfer function. Go ahead, please. Raise hand feature. Yes, Matthew, go ahead.
Is it G1 times G2?
All right, remember now, what you're doing is to state the systems in the inner loops. And I say multiply now, just state this, what components form the inner loop. We're trying to appreciate these terms by what is inner loop and outer loop. All right, so go ahead and see if we could speak to that.
So it'd be G1 minus H2 times.
Remember, no, we're not going to, sorry to cut you, but we're not going to use minus or plus, just state. So for example, you'd say, who are sitting, if we're in a class and we say, who are the person sitting on the first row? You just be calling by name, you know.
Oh, okay,
Jane.
okay.
Correct, go ahead.
So it's G1, H2, and G2.
All right, I'm going to come back to you. Thanks for your comment. Let's listen to what Jordan has to say. Jordan?
I would say the same thing, sir. G1, G2, and H2.
In the inner loop?
Yes, sir.
All right, fine. I just wanted to think. That's the purpose of me asking these questions, to think, all right? But let me now point to you what the inner loop is.
Sir.
All right, go ahead.
Just seeing the X in the circle, sir, so it'd be G2 and H2, sir.
That's correct, and that's correct as well, Travis. So what we're seeing here, the inner loop, I'm not going to define the inner loop. All right, let us hold a second here, Travis. What we're seeing here, we're going to now use a line to represent a loop. A loop means you can go in a complete circle. So let's watch this. And a loop is defined by a node, a summing node. So let's look at the summing node here. This defines the loop. All right, it defines the loop. Every loop has a summing node. Remember that. And so here is the loop. That's the inner loop. You might then ask, so what is the outer loop? Outer is the bigger one, and it encompasses the inner loop. All right, it encompasses the inner loop. So let's go one more time. The inner loop is found It's usually it's the smaller one as well, all right? So this one. Smaller mean in terms of, I should even say smaller because that's not a good term to use here. But the key to remember about inner loop is that it is embedded within another loop. So the bigger loop is this one. And of course, it's passing through an element in the inner loop. It's the bigger one, right? And you go do a circle around the outer loop, it encompasses the inner loop. All right, so that's one term you need to appreciate when you talk about block diagrams. Now, the other question I want to ask is, what is the nature of the feedback loop? So if I ask you, is the inner loop positive feedback or negative feedback? What we'd have to do is to look at the sign on the signal in the feedback loop. Here, the sign is negative, all right? Therefore, it is negative feedback. The same is for the outer loop. The sign is negative. So there are two negative feedback loops in this system. Go ahead, Jordan.
Sorry
Jordan,
about
go
that.
ahead, question. No problem. No problem. Right. So we have two loops. Now, to simplify this block, we have to now simplify the inner loop. All right. We need to simplify the inner loop. So we're going to be focusing our attention on the inner loop. Question is, what rule do we use to simplify that inner loop? Can somebody raise hand and tell me? Use a raise hand feature and tell me what rule do we use to simplify that inner loop? It's a feedback loop. How do we simplify that feedback loop? Yes, Antonio, go ahead.
Would it be the G2 over 1 plus H2 P2?
All right, so I'm going to write this time when you speak. Could you go right ahead again for me, please? You said that it's going to be G2 over
1 plus H2 G2.
G2. And you're applying the last rule that we looked at, all right? And that will be correct. All right, so let's go to the next slide and we're going to see the result. That is in fact the correct representation. So I hope that we're seeing how we apply this rule. We need to simplify a feedback loop. We have to apply the appropriate feedback loop reduction rule. Now, I'm now highlighting this section that we're going to seek to simplify. Reason being, we couldn't apply directly the feedback loop here because you see that we have two blocks in series. Are we seeing that, right? We have two blocks in series here, and so we have to take care of that part first. Now, while I'm seeing Travis presenting a solution, that's good, but I want us to appreciate the rules step by step in terms of how do we approach these systems, because they can in fact get very complex. Go ahead, Jordan.
So, sir, the X in between, that was in between G1 and G2, sir. You just ignore it now?
I suppose you're calling this X?
Yes, sir.
That's not an X, you know, it's a summing node. Sometimes it is written like this, plus minus. Sometimes it is written like what you see up there, but it's the same thing it represents, not an X, all right? Sometimes it's written like that, other times it's written with this thing in it, so it's not an X, okay?
Okay, all right, sir. I think
all right, yeah, man, sure, no problem.
Now,
sorry?
Sir, I thought with the X in it, sir, it meant that it wasn't going to allow anything to pass through it, sir.
Oh, no, it's a summing node, right? It's a summing, different way of writing it, all right? Okay, so I'm now saying to us that we're still seeing a feedback loop, and I can now draw a line to say, yes, this is a feedback loop. Again, why have a feedback loop? Because we have a summing node, and here is the loop. The loop is this, right? That's what happens. Now, within this loop, and we call this the forward path, all right? Another term again, the forward path. And what do you think we call this part down here?
Feedback, sir.
Thank you very much. So the forward path has two blocks within it. And so we need to now simplify that block. Now, what we recognize here is that these blocks are in series or cascade. So the simple solution to this is just to multiply the transfer functions for the two blocks. That's not difficult, all right? That's not difficult. And so the answer would be G1, G2 all over 1 plus G2, H2, all right? So here I'm showing you the steps that we're taking to reduce the block. So this is what we'll end up with after that last reduction rule. Now it comes to the point where we now have a simple feedback loop. See it here? And I'm saying simple, I'm talking about this in the form that we have it. One block in the forward path, one block in the feedback loop. Now, this aspect needs a little bit of attention. And let me see if I can do this. And so, what I'm going to bring your attention to is the transfer function in the forward path. What we do is to represent what we have here as a single letter. So you could choose a letter. I'm going to choose the letter, so I'm going to say let X. I don't want to, well, yeah, we can use X, but I tend not to use X because sometimes we use X for input, but I'm going to use X because you said so. All right, so let X equal G1, G2 all over 1 plus G2, H2. Why are we doing this? To prevent us from carrying around what would perhaps seem for some person initial stage a cumbersome function, and can in fact get much more cumbersome, or should I say much more complex than what we have here. So we're practicing how to simplify our procedure. So now this entire block up here is now represented by X. Therefore, I no longer treat this as G1, G2 all over 1 plus G2, H2, but as X. Having said that, what then would be the simplified expression for the function? Okay, can somebody tell me? Go ahead, please. Again, use the raise hand feature. What would be the simplified block? I'm actually going to draw it. So you tell me what should go inside here. Again, this is going to be R. I need now the of S, okay? For simple expression. Go ahead for me. What is inside this block? What's supposed to be inside here? All right, so I see, all right, I'm seeing something from, just let the one go. Roger, go ahead, please. So comment.
Good night, sir. It would be, well, x over 1 plus x times h1.
All right, and so that would be, in fact, correct. See, I think this is also Travis pointing that out as well. Right, so that is in fact the expression that will go inside the box. All right, so let's write this in. X, let me erase. I'm going to erase everything if I do that. X all over. Right, it's negative feedback, so it's going to be 1 plus X times H1. Now, here's what I'm going to have to, when I press the erase button in this particular feature, I don't know why it does it, it erases everything. I am going to explore other means of note taking, but until such time, let us continue. So we just found out that if we should let this be equal to X, the transfer function would be X over 1 plus X times H2. What we would now need to do is to substitute what X is in the expression here. All right, this is where now it will now begin to look like this. Are we able to, do we appreciate that? All right, so we can see that X is at the top here, G1, G2 over 1 plus G2, G1, G2 all over 1 plus H2, G2, that's right here. That is all over 1 plus, yes, X, and you can see X here again, times Am I seeing an H1 there? Correct, H1. I think I put H2 here by accident. I'm sorry. This is H1. This is the feedback here, okay? All right, so this should be H1. All right, hope we're seeing that. This is the feedback transfer function. All right, so I in error put H2 here in the first instance. So yes, we're seeing that the expression is worked out on this side in terms of substitution, okay? Now, how then do we simplify this polynomial, right? How do we simplify it into a form that has only one numerator polynomial and one denominator polynomial? All right, I'm going to show you one quick and easy way to do that. If we take this function here and we know that the numerator, this aspect of it, in the numerator we have the term 1 over 1 plus h 1 over, let's go again, this term right here. I'm going to try my best to bring out this point here. We notice this term here. I'm going to try to circle it here. That term is up there, and we want to collapse that polynomial up here. We want to collapse it. We want to make it into one single polynomial. So therefore, we want to multiply that aspect of it, or that the numerator of the entire polynomial. We want to. I'm coming to Raji. Just remember to go ahead, Raji, with the question.
So my apologies, I forgot to put on that.
All right, no problem. So what we want to do is we want to make the numerator, and because we have a double layer sort of a polynomial going on here, we want to bring this into a single polynomial, or should I say a non-fraction type polynomial. Okay, how do we do that? If we multiply this expression here by 1 plus h2 g2, it will cancel this aspect of it. I'm sure we can see that. But we also recognize that if we are to have the function maintaining the same value, or maintaining its form, then we have to do the same thing to the numerator. That's not a problem. Let's see what happens when we do that. So we're now going to multiply numerator by, so let's do that now, multiply by 1 plus h2 g2 all over 1 plus h2 g2. Let's put that g2 in place. Now we're multiplying by 1, because 1 plus h2 g2 all over 1 plus h2 g2 is 1. So now the multiplicative identity is applied. But look what happens. Look at the numerator up here. This will be cancelled. Look carefully at the numerator, other section now. This times 1 will give you, so I'm going to now rewrite. I'm going to rewrite. So this is cancelled, right? So it looks now like what we see here. Watch carefully. Multiplying this by 1 first gives us what? 1 plus h2g2. See it here? And when we multiply by the next term, there are two terms, one and under this year's other term. When we multiply this expression by the second term, it cancels this part of it. What do we then end up with? G1, G2 times H1. There we go. So it's a very simple rule that we apply. It works all the time by multiplying numerator and denominator by the term that is here, right? The denominator of the upper polynomial. Yes, if we multiply the function by that term over itself, which is what we did here, we would simplify the function quite quickly and simply. All right, any questions on what was just explained a while ago? Okay.
So I'm not sure if it's my internet, but it's blurry.
It's blurry. You're not able to, you look at using a phone.
No, laptop.
You can zoom in, you know. You can zoom in. All right. So if when you're zooming you're not able to see, then you know you can also let me know as well. All right. But beyond that, was the concept clear enough for you?
Yes, sir, clear enough.
All right, noted. Let's look at another block diagram. This one a little bit more complex. I'm going to ask you the question, how many feedback loops do we have in this function? In raise and feature, how many feedback loops do we have in this function? All right, go ahead, Antonio.
I'd say 3.
All right, we're saying 3. So 3 feedback loops. All right. So here we go. All right. Thanks, Antonio. You're in fact correct. You can close your mic now, Antonio. So there are 3 feedback loops. Let's look at them. And I'm going to start with the inner loops. All right. So these are 2 inner loops. I'm going to go with them. Either way, still inner loop. 1, let's do it right. 2, yes. And then the outer loop, the third one now, is the largest one, so to speak. It encompasses them all. So there are 3 loops. Now, here's the thing. We can't simplify any of these inner loops. Why can't we do that? Let's see if we can pass our pencil through the loops without interacting with any signal. So if we should take this loop and we go and we move through, we're seeing that there's a signal within the loop, and so we can't close it. Where do we put it when we close it? It can't float around. So we can't close this loop just yet because of this pick-off point. All right. Now, if we try to do the same thing, if we try to close this loop as well, it even gets worse. Well, it's the same situation. We have a summing node that is in the middle of it, so it can't work. Therefore, we now come to a point. What do we do? What do we do? Somebody asked earlier, what is the sense or what is the reason for moving pick-off points and summing nodes from input to output? This exactly is the reason. Now, for us to proceed, we would need to move either this node, summing node, or we need to move this pick-off point. Why do we need to move it? If we should move it, let us look at the situation if we should move it. If we should move it and place it here, it's no longer here anymore, what we now have is 2 blocks in series that we can now cascade. Having cascaded those 2 blocks, we end up with a nice looking feedback loop, which we can also simplify. All right, so that's the purpose of moving the pick-off point or the summing node. The same thing can apply for the summing node. Let's say we choose to move the summing node. Move it where? Where do we want to move it? We want to move it in a point where it simplifies the procedure. And in so doing, we could move the summing node from here to this point. So it would now be right here. All right, that is what we're speaking of. Okay, so here you could do either one. You could move the pick-off point or you could move the summing node. All right, so in the procedure we'll follow, what we're doing is to move the input of H2. Let's get this right. Input of H2, which is right here, pick-off point, to the output of G3. So what are we moving? We are moving the pick-off point from here to here. So it will now look like this when we're through. So let us see what the result is in doing that. And the rule would apply. Perhaps before we even go there, we could even ask ourselves, what do you think would the result be in moving our pick-off point to here? What should happen? All right. So if I were to go along with the same procedure that I was using, go ahead, Richard.
So if you move H, the kickoff point to G3, would you be able to form a loop then? Would you still have some summon bonds in that loop?
All right, let us move it first and then see what happens, because it may be difficult for you to see that at once. So let us see what happens when we move. So let us say, for argument's sake, we want to move this pick-off point. That's what we want to do right now. We want to move it from here to here. So it should look something like this, right? What do we need to do? There's something that needs to happen. Simply put, we are moving the pick-off point from the input of G3 to the output of G3, which simply means that the signal that we're getting at the end here would have already passed through G. We want to reciprocate, we want to cancel that effect. So we need to now divide by G3. All right, remember that rule? That's what we're seeing right here. Is that okay?
Yes, sir.
All right, good. So now, having moved that, we see that things get a little bit simpler. Look at what is happening here. We have two blocks in cascade that we can simplify. And you can look ahead and see that once we simplify these two blocks, what we end up with here is a clear closed loop that can also be simplified. All right, so that is the justification for having that rule. So we would recognize that when we cascade here, we're going to end up with G2, G3, and then we can now simplify the closed loop that will follow after that. So here I've just done that. All right, I've done that. All right. So having done that, and I'm hoping that we're seeing what is happening there. We multiply G2 by G3, and then we close the loop. And by the way, let me go back and show you what type of loop are we speaking of here. What type of loop is this? This is a negative feedback. So it must be 1 plus, there must be a plus sign in the denominator, right? Speaking of this sign right here. Are we okay thus far?
Yes, sir.
All right, good. So now things become much simpler. Once you get past that movement of the node or the stick-off point, things begin to look much simpler. So again, we have another cascade. Here's the cascade that we're speaking of. All right, let me redraw that. So I'm talking about these two blocks right here. Okay, and that's simple. Just simply multiply the transfer function of each block. That now becomes G1, G2, Z3 all over 1 plus G2, G3, H1. All right, that becomes this part here. And having done that, we could simply just call this entire block X. Let's use the term that was given earlier, though I perhaps wouldn't have used X, but it's quite fine. As long as the symbol was not used before, you can introduce it. Let X equal, right? So it's a let X equal, and you should always put this if you're actually doing a written question, right? Let X equal, and it goes G1, G2, G3 all over, and writing is not the best, but I have to just work with it. It's my handwriting. I can't go any further than this. G. All right, are we seeing that? That's it, right? That will be equal to X, and then you would simplify this loop right here. All right, it simplified that loop there, and we'll continue. So let us see what the next slides hold. So there we go. We simplify the entire forward path to look like this. Now I'm speaking about this aspect here. This aspect. We have to simplify that inner loop first. Okay. So when we simplify it, we end up with this. Now, you might say to yourself, okay, this looks like a feedback loop. But what about the transfer function for the feedback? I'm not seeing the transfer function. How do we proceed? Simple. There's a feedback loop, but it's called unity gain feedback. All right, so when there is no block in the feedback loop, it's simply called unity gain, and for the very obvious reason, right? The gain is 1, so I've just put a box in there with 1 in it. So therefore, when we're simplifying, if we're going to call this, we can't call it X again because we define X as something else down the road. So could you give another letter, please?
Why, sir?
You.
Why I couldn't use Y?
So because it's output already.
Correct. Correct. So
Oh,
you have to
the
use something
why.
else. Yeah. So what I heard somebody say something now. What
You.
letter can A? So
You.
you're gonna what? Let what?
I said you.
Oh, U. All
And
right, fine. Let U equal, and it's going to be all of what you have right here. I'm not going to write it because I don't have enough space with my very unique handwriting. So U would be all of what is expressed here. So what is going to happen is that the transfer function, if we're going to call this U now, it's going to be equal to what? So y over r is equal to, let's do this again. It's actually what? Negative feedback. So it becomes u continue over, I think I was speaking a while ago. Go ahead and continue this solution, please. It was
1.
Go ahead. 1 what?
So is it plus
1 plus
plus
Mhm.
plus
1 plus u
That's it.
UG
Because h
plus
is 1. H is 1, as what I call h is 1. That is it. That's it. Right? And so now when we substitute what u is in this, and we carry out the simplification I expressed to you earlier, we'll end up with this final result. So again, u would be all of what we have up here. Yes, all over 1 plus the same thing here. And again, I say to you, what you're going to do when you end up with that expression is to multiply numerator and denominator by this term. And everything will come down to look like what we have here. Okay, so we will have, I'm going to allow for you to do some practice, and we will have a session, a tutorial session where we work in more detail. I'll obviously have more whiteboard space to work with. Here's my slides, and I don't have much space here, but in the tutorial sessions, I'll be able to pull out a screen to do that. All right, so that would cover the what I call an introduction to block diagram reduction techniques. And so far we have used all except one. We moved the pickoff point. We haven't moved a summing node just yet, but it's the same procedure. And bear in mind that in the example that we just did, the option exists for you to move the summing node instead of the pickoff point. So there are a number of ways to get at the same solution, right? It comes like it's just no way like math. There are a number of ways to carry out a procedure. As long as they are legal, you will end up at the same point, regardless of what route you take. Okay. Now, before I move over to the tutorial session, I'm going to just provide an introduction to a software called MATLAB. Now, maybe some of you are already familiar with MATLAB and how MATLAB is used or what it is for. But MATLAB stands for Matrix Laboratory. And MATLAB is a very powerful interactive tool that is used for numerical computation and visualization. It is a software that is extensively used, particularly in controls engineering. All right, any engineer that you meet up that is practicing engineering in the true sense, and I must be careful I say that. Let us start with design engineering, okay? Then they would say, yes, we are familiar with MATLAB, okay? And especially controls, there's no way you can go through a controls course without interacting with MATLAB. All right, what it allows you to do is to provide some simulation. It provides you to model systems and to then provide simulation results. Okay, it doesn't work in the same way that your, what you call it now, your workbench. I keep using the term workbench, but I can't get the correct term. Could somebody again tell me what's the correct term for what you use as electronic circuit simulation? The software from National Instrument. What's it called again?
Multisim, sir.
Multisim.
Multisim.
I can't remember. Multisim. When I was using it a few years ago, it was called Workbench. Okay, so Multisim. It's not the same way as how Multisim works. Multisim is a graphical based program in the sense that it uses graphics to represent the elements, but in MATLAB you actually use matrix, right? So you use vectors and matrices. That's it. Everything that you express, no matter how complex the system is, it comes down to vectors and matrices. That's how we express these systems. Okay. Of course, you can define a system and then give it a symbol, but in the background, you're actually fundamentally using vectors and matrices. Right. All right. So it really adds, with our simulation software, it allows for quick simulation and modification of systems while you test them. Okay. I'm going to just demonstrate here what a typical analysis with MATLAB would look like. So you recall this network that we looked at in the previous 2 weeks ago. Last week we had a situation where we had no power. So for the previous week we looked at deriving the transfer function for this network, and we also use the transfer function to derive the unit step response. That is what happens when we close the switch, having a 1-volt source as the input signal. Now here we're giving this circuit a little bit more character. We're making it unique in that we're providing the values of the components. In the example that we did, we had generic terms, C and R. Here we are having specific values, R being 20 ohms, C being 0.1 farad. Let's see how we analyze the system in MATLAB. So recall that the transfer function for the system was this, 1 over CRS plus 1. So what do? We substitute for C and R. C, I believe it was 0.1 farad, and R was 20 ohms. Hence, we have a unique transfer function being 1 over 2s plus 1. Now, that is the transfer function for our RC circuit. How do we then put this into MATLAB? MATLAB, as I said before, only sees vectors and matrices. Let's proceed. To enter the transfer function, that is actually a polynomial here, this is a polynomial. Into MATLAB, we enter the coefficients of the numerator and the denominator as vectors, okay? And it's done in a particular order, descending order, okay? So let us take the numerator. Numerator is 1. What does that imply? A vector that simply is 1, right? How about this one? 2s plus 1. What does that look like as a vector to be put in MATLAB? Start with the highest term. Highest term is that associated with s. What is the term or the coefficient of the term s? It is actually 2. Going down the line, what is the coefficient of s to the naught or s to the 0? That's actually 1. Okay, so I've just converted the polynomial form into vector form. And now in MATLAB, we could define these terms, numerator, denominator. Let's put num, then, you could call it any symbol at all you want to call it. All right, I could put n, doesn't matter, as long as you use non-code terms, okay, non-specific terms, I mean terms that are dedicated for specific operations in MATLAB, okay? So we're saying, coming to MATLAB, we have num, then, and we're using some special MATLAB features now. We're saying to MATLAB, we're going to call G the transfer function that is defined by this term, numerator and denominator. Then we're saying to MATLAB, derive or obtain for us the step response of the system, and please to provide a grid on that response. Go ahead, Matthew.
Yes, sir. You mentioned that we should use the greater number, which of like the 2 and 1. So we should put like 2 first. So is there a scenario where 2 is less than, for example, the other variable or the other number?
All right, thanks for that question. When I say descending order, I'm speaking not of, I'm talking about the coefficients. So with a polynomial, let's say a polynomial of x, all right? The smallest coefficient is that, the lowest term of the coefficient is x to the naught. What would be higher than that? X to the 1, x to the 2. You see where I'm going with this? What just happened here? X to the 3, and so on. Now, in this particular situation where we have 2s plus 1, right? It's a polynomial. The highest term in the polynomial is what order? 1, s to the 1. So we start with the coefficient of the highest term and we go in descending order. So I said enter the coefficients of the numerator and denominator in descending order. So the coefficient of the polynomial is what is multiplied. So the 2 is one coefficient here as well. S to the 1, S to the naught is actually 1. Is that okay?
Oh, yes, sir.
All right, good. Any other questions here? Travis, go ahead. Travis said what's grid for? All right, I'm coming to that. Manchester, have a question? I guess
Oh,
not.
no, sir. No, sir.
All right, yeah. So what is grid for? We need to let's see what that is for. All right, let's move to the next slide, where we should be seeing what MATLAB is going to do with that code. It's a code. Let me clean this up. This should just give me back control of my screen. Oh, I think I lost my pointer. All right, so really, are you hearing me still?
Yes, sir.
Okay,
Yes, sir.
my screen, thank you. My screen is okay. My screen got frozen a while ago. I'm not sure what reason for that. Right, so this is actually the MATLAB code, right? And we're going to now see what MATLAB does with that. Here it is that MATLAB has now generated the plot. And the question was asked, what is grid for? If you didn't put grid, MATLAB would not put this sort of a grid network in the plot. Now the grid serves for us when we're analyzing the plot. So for example, we know about time constant, and quickly could somebody tell me what time constant mean, please? See if I could zoom in here. Time constant, the time for the system to reach to what? Uh-oh. Go ahead. Okay, 6.63 or 63% of its final value. So if you zoom in with your screen, if you could zoom in, you would see that looking for the point 0.63, it would correspond to what? About 2 seconds. Are we seeing that? Confirm, please. Anybody?
Yes, sir.
All right, let's go back to the function. What's the time constant with our in terms of RC network? Is equal to R times C. And so when you multiply 20 by 0.1, what's the result? 2. So that's one way to confirm that, yes, something is happening that is consistent with what we know about RC network. The question also could arise is, how long does the system take to get to its final point? It roughly takes about 5 times constant to get to 99% of the value. So 5 times 2 is 10. All right, so if you look at where 10 is, it's actually about 99% of its final value. So here, by just simply putting in this code, we can now analyze the response of this system. All right. Now, in subsequent lab activities, you will be using MATLAB to perform analysis of various systems. It's no different here for this mechanical system, spring mass damper system, where we actually, in the last session, we derived the transfer function. Given the terms in the system specific values, we end up with a unique transfer function. And again, this time we're not going to necessarily find the step, but we're finding the impulse. What would happen if we should hit this mass with a high, with a large force for a very short time? And let's see what MATLAB generates. Again, grid is there. We can see that the mass quickly extend to about 0.6. Let me see if I'm seeing this clearly. About 0.7 meters. Again, this is based on what the math is saying. All right, 0.6 meters extended by 0.6 meters in roughly about takes about roughly about 2 seconds to get to that maximum point, and it oscillates for a couple of cycles, and then it finally settles back down to where it was initially after about, say, nearly about 20 seconds. So we could say that the mass, remember our output in the system is the mass displacement. So what we're actually seeing is what happens to the mass displacement over time. Yes? So you hit that spring almost like a suspension hitting a pothole, and if it doesn't have good shock absorbance, shock dashpot damping constant, then you're going to have a lot of vibration happening, and it takes quite a while. So imagine if you hit a pothole in a vehicle, and 20 seconds after hitting that pothole before the vehicle comes back to any sense of steady state. I'm using the term steady state here, but the term of normal movement, okay? That's exactly what we're doing here at MATLAB. We derive our system, put into MATLAB, and we see what happens. Now, in terms of design, let's say you design a suspension system. You could go back and adjust the dashpot constant. You could adjust the spring constant and observe the variations. We can do multiple plots on the same graph to observe the effects of bearing a particular term or a particular constant in the system, right? Any particular section in the system, you can adjust and observe the effects of it as it relates to system design and analysis. All right. Go ahead, Antonio.
The question may be a bit unrelated, but so that you were designing a shock absorber, so I wanted it to go to its steady state in like say 3 seconds instead of 5. How would you go about mathematically getting the answer instantly instead of doing parallel?
All right, so right away you're going on to other lectures that we have coming up. So I'm going to ask that you hold that question for a while, and then we'll have a look at it in subsequent lectures, because there are methods for us that would guide us in making adjustments in getting to this, right? So what you have just quoted here is a design criteria, right? And it is called settling time. And I can't speak to it now because we have not yet covered that, but it's a very good question. How do we design towards a specific settling time? And there are ways to do that. Very good question, all right? But we're going to look at that in subsequent lectures, all right? All right, so at this point, we're going to stop this presentation, and then we're going to move over to the tutorials. Go ahead, Richard. Question?
So, is there I was using the MATLAB today, and I came upon a thing called system toolbox. I'm not sure if you're familiar with that portion of MATLAB.
Yeah.
It is I need a license and stuff for it. Is there any way to go around that?
I can't speak to your specific situation, but what I could say to you at this point, Mr. By now you recognize or should know that Mr. Matthew Lin is responsible for labs. He'll be taking you through the exercises. Any questions you have on labs, you're going to direct them to Matthew Lin, right? Why am I saying this? You're going to do some labs with MATLAB, and he would guide you accordingly. But to say this, persons who have UTech email accounts will have access to, I think it's full access, to MATLAB through the university's license. So if you need to, you will need to get access some means, whether through a trial version, which you'll use for the duration of the module, or you could go the route of getting the license, access to the school license through your UTech email account. There are two options, but you could get further details from Mr. Lin on that matter. All right, so just to note that. Is there a question? Did I see somebody raising a question? Additional question?
Is the one with the marking the labs?
Yes, you'll be the one assessing the labs. Okay. All right, so
it wasn't a question, sir. We was just adding to what you're saying, same can probably, because what I did, sir, was log on to the MATLAB, MATWorks, and then use my UTech email and then request access, and eventually I get the access to the UTech email.
And it's full access?
And then prompt for download whatever version. Yes, well. Yes,
as
sir.
far as you know, you have all the features that you need to use.
Yes.
All right, so just to and thank you for confirming that you will get full access. All right, once you have a UTech email account, and so you wouldn't have to worry about expiration. It is working as long as UTech version is up and running. All right. So at some point, you'll be guided further on that, or you could talk to your colleagues on how they were able to get through with that. All right. So Roger, Roger, I want to go to share that. Roger, sorry. Who just shared the
Yes,
experience?
sir,
Good. So Rajiv can perhaps provide some information. Beyond that, though, the lab technologists will provide you with that additional information. All right, so I want to now move to the tutorial. Now, there are two worksheets out. The first one, are there any concerns about the first one? By the way, the test will cover, and this is something that the test is next week, this at 7 o'clock. That's during the class time, 7 p.m. I should have posted, but the test will cover everything up to the lecture covered in the last presentation. It's lectures 1 and 2 only. Okay, so lectures 1 and 2 only. What I will do, I'll try to provide some information. I'll provide information as to what the tests will cover each time. So there are 4 tests to be done, and each time I'm going to provide you with the topics that will be covered in the assessment. Okay. So having said that, there are 2 worksheets out. Are there any concerns with items in worksheet number 1?
No.
No. All right. So how about worksheet number 2?
I'm not sure. I forgot very far yet.
Hello? Worksheet number 2?
So you posted worksheet number 2, sir?
Really go through it as yet, sir.
That's an interesting
I've
question.
forgotten very far in worksheet number 2 as yet, sir.
You know, so when was the test due again? There was a test. I think there was a test for today now. You might saw that.
Yes,
So
sir.
what were you planning to do?
Yes, sir. I
Sir,
saw
whenever
that.
Oh, you anticipated that the test would be postponed, no? That's what you did. Oh, I see. This is what you call predictive analysis. And what a thing if I say, you know what? Anyway, you know I wouldn't do that. So, you think when it work out to a T. All right. So anyway, it's kind of unfortunate because you'd have needed to go through, as I said before, I do my thing a little bit different. I want you to attempt the worksheets and then come with a background. I don't want to be teaching in a tutorial session. The tutorial session is a session that is geared towards assisting you with challenges. Is that clear? Okay.
Yes, sir.
Are you seeing on your timetable a session on Wednesday for tutorials? Anybody? That sounds like a negative. That sounds like a no. Antonio?
Wait, I have a tutorial tomorrow for you.
Somebody else talking.
Okay, noted. Anybody else?
At 1500.
You can go ahead now, sir. I did question 1, A and B. I attempted question 2.
That's for which sheet? Which worksheet?
Worksheet 2.
Worksheet 2. All right, let me bring up worksheet 2 since you're bringing attention to it. Let's bring up worksheet 2.
Sir, quick question. As it relates to the all right, what do you call it? Servo. It's SERVO. Say a drone can be like an example, sir. The stabilizer on one drone.
You're talking about server systems. A drone is a server system because it is following a constantly changing input command. So the drone is not going to stay in one place and just, well, the drone can be in hover. Hover meaning it stays at one point and just simply resist any movement due to wind, all right, wind gusts. That is one state which is in regulatory control. But generally speaking, the drone is a server system. And the reason for that is because it is constantly receiving updates of a changing form. You're constantly telling the drone to go in a new direction, right? So for example, you're moving the drone from point A to point B, you're giving it updates that are changing over time. And so the answer to your question is yes, a drone is a servo system, just like an aircraft is in terms of how it's navigating from point to point, point A to point B, a servo system. Input commands that dictate its new position is constantly changing. Is that okay?
Yes, sir.
All right. All right, let's see if we could find the it's a PDF. It's a PDF. All right, let's all right, are you seeing the worksheet too now?
Yes,
Yes,
sir.
sir.
All right, good. Now I can't see the raise hand part. I'm just seeing the full sheet. So anyway, let us see if we can get through this. So let me use the time. We have about half an hour. Two questions. There are about 3 questions. So this question here says, derive the transfer function for the RLC circuit. A, relating the input VI and output VO. All right. So any suggestion how to proceed with deriving this transfer function?
Use KVL and you get a general voltage expression, and then you replace the terms that you don't want. So you would replace VR with IR, you replace VL with LDI DT, and you keep the VC and the VI.
Okay,
Then
great.
it's more arithmetic. It's difficult to explain in words.
No, man, it's quite fine. Those who do their homework would know that you're talking along the right line. So let me do what you just said. You said this is an electrical network. Based on what I expressed to you. By the way, there are a number of ways, in fact, 2 general ways of deriving the transfer function. One that I thought I'm going to do right now, one that I exposed you to rather, is the one that I'm going to do right now. And what we said is that it's an electrical system, so we apply electrical laws. What do we know about this network? All right, what do we know about this network? It's a series network. The same current passes through all the elements in the network, and the network voltage drop is defined by Kirchhoff voltage law. So we could say that, and I'm not going to put the function of time, I'm going to put VI. I'm going to do it like that, VI of t. I'm sorry, I'm going to do it so that's that the persons who may not be aware. VI of t, called Kirchhoff law, is equal to VL time function plus VR of t time function plus VC of t time function. That's Kirchhoff law, right? So I could just put K VL, all right? Kirchhoff's law. Now, what 2 variables do we want? Again, right now I'm actually teaching. Yeah? What 2 variables do we want? According to what was just said, which is absolutely correct, we need to have 2 variables in the expression for us to proceed with deriving the transfer function. What 2 variables are these? What are the 2 variables?
VC or VO and VI.
That's correct. So what we want is VO of S over VI of S. Whatever it is equal to, it is going to be our transfer function. That's what we don't know. We want to find that. So we're interested in keeping VO, and this is supposed to be VI. Let's use the common I. All right. Should be able to erase this by itself. Wonderful. All right. So VI of S. So looking at our first expression as Kirchhoff voltage law, we're seeing that we have a number of variables that we don't need. Namely, that's a question now. What do we need to replace?
VL and VR.
VL and VR. It didn't said VC. Why did you say VC too?
VC, you're measuring VO across the capacitor, so you want VC.
So VC and VO are equivalent. No, so you say it's same to me, yes? VO and VC, they're the same. That's fine. All right, thank you. So let us now proceed. What can we do? What can we do? Let's take, for example, VL. What do we know about VL? VL is equal to L di of T dt. I'm speaking about I here. We also know that VR is equal to I times, I'm going to put, sorry, I of T, I just keep consistent. Here I'm trying to help you to appreciate what the variables are in the function. I of T times R, and we could simply put VC of T. Let's keep it like there for now. I deliberately want to keep it there. If we put VO, it's fine, but I'm keeping it as VC for now. All right, but we're concerned here now with focusing on VL and VR as was pointed to earlier. So now we did some substitution, yes? And we're seeing a new term called I. Do we want to keep I? Do we want to keep I? I is not a part of what we want to keep, so we need to now find a way to replace that. All right, how do we replace that? How do we replace that? Any ideas?
Repeat the question, sir.
And the Laplace.
We are seeking to get an expression, a differential equation that only has two variables, VI and VO. At the moment, we have an expression. I hope you can see that expression. And it has two variables, I and V. Well, I'm sorry, it's three variables. Let me careful to do this. All right, three variables. Now, of the three, technically speaking, we're keeping this one. The others need to be replaced. So what do we know about I of T? Any way that we could replace I of T?
You know, I of T is C dVC by dt.
So we know that the capacitor voltage, or sorry, should I say, the current through the capacitor. By the way, I'm hoping that we're seeing that the same current passing through all the components. So I could therefore write, we know that I of T is equal to I C of T, which is equal to what? C d VC of T dt. So the capacitor current is equal to the capacitance times the rate of change of the capacitor voltage, VC. Okay? So wherever we see I of T, we can replace it with C dVC of T dt. Let us proceed to do that. If I were to be numbering my functions, I could be calling this 1, be calling this 2, and so I could now substitute 3, which I call this here, into 2. In so doing, what I will end up with, and I'm going to write it here, is that I'll end up with VI of T is equal to, let's do this right now. Let's do this right. Is equal to L, and what's going to happen here? I'm going to now put this is C. So what I'm doing is substitute this I here, which is C dVC of T dt. So it's going to be a double derivative of this function here. Are we seeing that? dVC of T dt, double derivative, plus C dVC of T dt times R. I should have put the R before here, so all right, that's cool. Plus VC of t. Any concerns with what is here? I hope we can see what is happening on the function. Are we able to see the mirror of this out and write it more legibly? So this is r times c times dvc dt. All right, so are we able to see that?
Yes, sir.
Good enough.
So the question
So
on the
now,
BC for square or the D for square?
I'm sorry?
For the first expression for the
It's a double derivative. It's somewhere up here. All right, but I'm sure you understand it's a double derivative. We're not squaring anything, you know. Remember, I should be careful. This is not we're squaring
Yeah,
it.
that's
We just
yes, sir. That's what I'm
hello?
saying. You had the squared, sir.
Uh-huh.
No, I
Is it
said that
okay
you had
now?
the square and the VC. Yes, sir. It's fine.
All right, thank you. So now, how many variables do we have? And do we have the appropriate variables in the expression based on what we want to satisfy? Two variables need to be there, vi and vo. Do we satisfy that now? All right, since you're not following, vo of t is equal to vc of t. We already established that. Somebody pointed that out earlier. All right. And so, yes, we certainly do have that because I can now go ahead and change all of my VCs to VO. Yes, so I would, and because if what we should be able to appreciate now, instead of writing this all over again, I'm just going to go ahead and write VO wherever I have VC. And so we're good. We're all good. Okay. Now, what's the next step?
Sir, put get VO over the left side and get it in terms of VO over VI.
All right, I hear the clicking on, I'm sorry, I heard your comment, but I'm also hearing clicks on the, maybe the raise hand feature, but because of the view I'm looking at right now, I'm not able. All right, good. I can now see it. I just bring it back up, but to make my screen so small, I won't be able to write as easy as I could. But I hear myself put in terms of something you want to keep. It's the old statement. Bear with me here as I navigate the space. Could you repeat the comment, Jordan?
Oh, sir, yeah, I was saying that to get the left hand side to be, after you substitute VO for the VC, sir, you can get the left hand side to be VO over VI.
You know what is happening if you do that? You're going to get into trouble, you know. You're trying to somehow, you can't move anything right now, to be frank with you. But you have to do something very important.
Sir, fuck
right? But it's the same thing. I think they were saying you have to take the Laplace. All right, you have to take the Laplace. That's what we have to do now. So we're going to now take the Laplace. I'm going to try to zoom this in. We're taking the Laplace. So let's take the Laplace. I'm going to write the Laplace solution just about here. Okay, so focus your attention. I lost my pen. All right, so let's try to do it like that. So I'm not able to see the screen anymore, the comment. So we are now going to take the Laplace. All right, we're going to put it right here. Laplace of this aspect of this term here is going to now give you V, capital V, I of S equal LC. Go ahead for me. Somebody could just open your mic. I'm not able to see who, but just open your mics and proceed to tell me what's next, please.
It would be S squared, sir. LCS squared.
S squared. Continue.
Plus RCS.
Hold on. We take the Laplace right here.
Or V over
Something missing. V O of S. Continue now.
plus SRC.
I'm going to put RCS. It's the same thing, same story. Continue. VO of S. Yes, continue. Plus VO of S. Now you might ask, why did I put the term RCS before the VO of S? why I do it this way, because RC and LC, these are constants, and these constants will go before the terms in the polynomial. But that's one way to write. That's the better way, I believe, to write it. Put these terms before the functions, all right? Because what you're going to find is that these are going to be the terms that form the coefficients of our polynomial in the transfer function. But let us proceed and we'll see what exactly is it that I'm talking about. So continuing, we can now go ahead and factorize, as you put, or group the like terms, all right, and then factorize. So how do we then factorize? What are the factors that we're seeing in this?
V O
V of S.
V of S. That's the main thing. It's right throughout. See, it's occurring right here. It's occurring right here. It's occurring right here. So we can factor it out. So when you factor it out, what we end up with? Quickly, go ahead for me, please. You know how much time?
LCS squared
Mm-hmm.
plus RCS plus 1.
Plus?
1.
Plus 1. Good. All right. So hoping that we're seeing this. All right. We should be seeing that. And so now we can now write VO over VI. And this is of S. It's equal to what? 1 over. And this is the polynomial I was speaking about earlier. LCS squared, right? Plus RCS plus 1. And I've written it in descending order. The polynomial is written in descending order. S squared, then S to the naught. So can somebody tell me, those who did the worksheet, is this the result you got for the transfer function for the RLC network?
Yes, sir. A bit altered, but the same thing.
Could you repeat that, please?
The same thing. Just that I had made the S squared term 1.
Oh, all right. So, and that is also fine, because you're going to find in some cases we need to make that. But for now, for not to confuse anybody else, but that would be quite fine. And so to do that, you'd have to do what? Divide throughout by what? And just to satisfy what you just said, let me see if you end up with what I'm going to be getting now. So if you want to get the L squared term, you have to divide numerator and denominator by LC. So that'll be 1 over, let's see if I'm doing this correctly, LC, and that'll be S squared plus RC over LC, that cancel, S plus 1 over LC. Does this look like what you have?
Yes, sir.
Okay, so that's one way to write it. No, nothing is wrong with this. Nothing is wrong with what you have here. But this is quite fine. This is what you'd probably find in probably most cases. But the point I'm making here, they're equivalent. I don't know if I should do this. There's one other way to let me ask. Any questions on what was just done a while ago? Any difference in the result that you obtained when you tried it?
No, sir.
All right. Anybody found any other way to analyze this network using deriving the transfer function using any other method? Let's see who is in the participation list. So that's the way that you use it. I can tell that some persons didn't go through it, you know. But anyway, questions of similar nature will be coming on the test. The test is going to be for an hour, but the material will be able to be covered in 45 minutes. All right, so the 15 minutes is right. Go ahead.
Sir, would you get the same marks?
The same what?
Would you get the same marks if you transfer check the Laplace transform of the elements and then just apply circuit theory, like you change L to SL
and C to 1 over SC.
All right, that's what I was asking about method. All right, so I'm going to erase what is on the screen at the moment and just to perhaps expound on what was just asked a while ago. So another method that can be utilized, I'm going to erase this what's on the screen now. All right, there should be enough. Where's that feature? All right, in the absence of that, let me do something quickly here. So, all right, this is pretty slow already. All right, so increase the screen here. When we look at this network, we can actually treat it as reactive and components, right? So I'm looking for the erase all feature, but anyway, where's my marker now? Okay. Interesting. All right, so when we look at the network, you see, we could treat them as reactive components. And so there's a way I could show you, but let me see, I have about 15. All right, so for the capacitor, when we look at the voltage drop across, you know, the expression for the capacitance, this is VL, VR, VC. We know that IL is equal to VL, my apology, is equal to L di dt. All right. So if this is the relationship without considering that the initial conditions are 0, what we have, if we take the Laplace of this expression, we end up with VL of S is equal to L over S I of S. So based on reactive formula, which is V over I, we end up with, let's see, oh, my apologies on this. I made an error. Let me fix that. Let me fix that. So let's go back again and take the Laplace. Not sure what's happening here. Let me fix that. So taking the Laplace of this here function, this is the function that relates the capacitor voltage, the inductor voltage with the inductor current, IL of t. All right. When we take the Laplace of the function, what we end up with is VL of S for this part is a time function equal to L, and because it's a derivative of IL of t, we end up with S times IL of S. Now, from this expression, we know that capacitive reactance is voltage divided by current. Therefore, when we have VL of S over IL of S, it is equal to L times S. Therefore, in terms of writing the circuit components in terms of the Laplace expression or in the Laplace domain, we would just simply write LS. For resistor, it doesn't change. You can go through under the same thing I did just now. For capacitance, it actually is 1 over CS. Again, you can do the same thing I did here by writing the expression for the capacitor voltage and current, which is VC is equal to, let me actually write it, I'm a visual person. So for the capacitor, IC of T is equal to C dVC T dt. Are we seeing that? So if we now take the Laplace, what we end up with is IC of S equal what? CS times VC of S. I'm going to do the whole. You can go ahead and do that expression, all right? I'm just showing you how we end up with these terms for the represented reactants in the S domain. All right. I wish this had an erase all feature. See the difference? Anyway, so having that sort of a expression, how we would proceed, you see, is to use the same kind of Kirchhoff or the laws for the circuit rules. We apply them. So I guess maybe I should ask the individual who raised the question to tell us how we would proceed. Having recognized, as I just pointed out to you, the the reactive representation in the S domain. So in time domain, we have L, we have R, and we have C to represent these terms. But in terms of in the S domain, we want to express them in terms of a reactance. This is what we would do. LS for inductor, R for resistor, and 1/CS for capacitance. Then what do we do next? So I'm going to ask the person who raised the question to come back and to share what it is that was done to derive the transfer function from there.
Okay, so we already have the Laplace of each element, so recognize that the output voltage is taken across the capacitor, and all the elements are in series, so can apply voltage dividable. So we're going to put the 1/SC on top, divided by the sum of all the resistance in the loop, and then we'll simplify the expression.
Okay. So you're treating it now, again, as I said, thank you for that. Don't close the mic just yet. So you are now using the voltage divider rule, all right? That's one. Once any rule at all that you use for circuit analysis and treating these components as reactants, you'll end up the same point. All right. If you want to go and find I in terms of these components, which is the sum of the reactances divided by the voltage, yes, and then multiply it by the output reactance, same story. Okay. All right. So thanks for that. Any concerns or questions along that line? Anybody?
Yes, sir. Just confirming. Regarding the first worksheet, I used the information from the first lecture slide to answer those questions. We wouldn't have to do any research outside of it to answer the questions.
Of course you would. I mean, if the notes are providing some foundation work, you know, and anything that you do should not go too far from that. So to say that my notes are in themselves complete and sufficient, I would not necessarily go to that point. So for example, let's say in my notes, I provide you with, so for example, today in the presentation, I provided you with some examples, but I did point out that the example did not cover, yes, the movement of a summing node. Yes. So let's say you wanted to do a practice with the summing node being moved. Perhaps you could look at a question online, or you could try it based on the rule I gave to you. Let's say, for example, a person raised a question about a drone being, is it a servo system or not? Fine, my notes may provide you with some information, but it may not be sufficient for you as an individual. This is where you need to take a textbook out and read to supplement what I present to you. It helps to galvanize your understanding, the concept that you have in your mind. If you begin, and by the way, what I'm actually saying to you right now is this. Please do read. Don't take what I present in my notes as gospel. Go and read additional material, and it helps you say, okay, I'm seeing a connection here. I'm seeing this, both materials saying. And if you do see anything that is not supported in my notes, I would love for you to come and share to say, so for example, I did not present to you the method of using the reactances in the network, but somebody went ahead and did some work, and I appreciate that, right? And that is how I expect you to proceed. Now, I'm not saying you should go and read up every single control system book because time does not allow for that, but keep it within the scope of the notes and the worksheets. So this individual went ahead and looked and said, okay, how do I simplify, how do I derive the transfer function for this network research? And they said, oh, I'm seeing a method here. Let's see, let's investigate it. And I don't have a problem with that. Okay, the method is quite fine. The only issue is that if I ask you, if you're asked, not necessarily me, but if you're asked to derive a particular function in a particular way, then you have to use that method. Okay, but I hope I am clear in terms of how you utilize my notes and so forth. All right, so I do encourage that you read additional material, not to go beyond what the objectives are of the lecture slides and the course outline. Don't go beyond that. All right, certainly that is not going to be helpful at this moment. Is that okay? All right, great. All right, so we are up to the end of the session, and the fact that there are no other burning questions, I suppose that you are ready and rearing for the final exam, the test on Tuesday coming. All
Sir,
right?
for the test, you
Travis,
need MATLAB.
no, you don't, because MATLAB was not covered in the first two lectures.
Oh, okay. Thank you.
All right, cool. All right, so take it easy, and we will link up again next week. This time, I think we need one.
Sir, we're supposed to talk at the end of the class.